It's a pleasure to be here. I also thank the organizers for organizing this wonderful meeting and for giving me the opportunity to give this talk. So I'll be talking about how to explore the black hole interior using traversable wormholes. And my talk is based on a paper that Gao, Jefferies, and Wald wrote, a paper that we wrote with Douglas and Shenbin Yang, and also another paper with Joanna Corcoquolo. So as Douglas reviewed, the SYK model and nearly ADS2 gravity are two theories that have similar low energy properties. So it's not that there is an equality here, but they have similar low energy qualities. And in particular, they both have an emergent reparametrization symmetry, which is both spontaneously and explicitly broken. It's explicitly broken by the actually, I had the PowerPoint thing where I could. Is this the PDF or? Okay. Okay. And this fact, so this realization of the symmetries, dominate many aspects of the infrared dynamics, such as the low energy, the low temperature entropy, so that it's linear in the temperature. So many aspects of the gravitational back reaction, including this chaos exponent. And one part that we are going to concentrate on here is that it also governs the wormhole traversability and also the precise location of the horizon. I mean, it governs that because it will govern the precise location of the horizon. And now in nearly ADS2 gravity, I'll review now that this Schwarzian action is describing the motion of the boundary in ADS2. So we have very simple gravitational dynamics in this nearly ADS2 space. It's governed either by this Yakib-Teitelbaum gravity theory, or you could say the Schwarzian action. And the point I'd like to emphasize now is that we can think of that as the motion of the boundary. So we can think of this dynamics given by, let's say, coupling Yakib-Teitelbaum gravity to matter as follows. So we have a rigid, completely rigid ADS2 space where you can have some matter fields that are propagating. These matter fields do not cause any deformation in the metric. And then we have some boundary. We normally think about the boundary in ADS-CFT as well being at infinity, right? But here it's convenient to think of the boundary as being at a finite but large location. And this boundary has some dynamics in the sense that it represents a particle moving in ADS2. Following some local dynamical laws. So you can think of this as a massive particle in an electric field, so that's why it's sort of accelerating towards the boundary instead of falling into the ADS2 space. We can also think of this as the kind of UV brain as in a Randall-Sundrum model. And the motion of this boundary will encode all the gravitational effects. So these matter fields are really are subject to gravity, but they are subject to gravity only through the motion of this boundary. Now the theory in addition has some constraints. So what links the matter fields to the boundary is that the total SL2R charge of the system should be 0. So this is this SL2R is the group of isometries of ADS2, and the net charge under those symmetries should be 0. Those are gauge symmetries. They are part of the diffeomorphism symmetry of the system. And this is, in fact, would be a linear combination of constraints of the constraints we have in general relativity. So those are local constraints, but we integrate them against the Killing vectors. And we get these global constraints, which tell us that if we, for example, calculate the SL2R charges of the matter here, and one of them, for example, is the time translation symmetry, conjugate to the translation symmetry in global time here, for example, that's one of them. And we add them to the similar charge for the left boundary particle and the right boundary particle. They all should sum up to 0, and in this way they are linked. Now I'm going just to give you an example for how this works. So, for example, you know that if you have a black hole and you drop in a particle, the horizon moves out. What this means is that there was a region that was visible from the boundary before you put in the particle, and it's not visible after you send the additional particle. So, for example, let's say we have a black hole, and we have some event here, and this event is visible from the boundary. And now, at this point in time, we send in a particle. So we send in this particle into the black hole, and what happens is that this particle gives a little kick to the boundary trajectory, and this kick is enforced by demanding that the SL2R charges are conserved here, and that condition essentially saying that the energy momentum of these particles are conserved as if they were particles moving in a fixed ADS2 space. So they behave as you naively expect. So if you send a particle here, the other one is kicked in the other direction. And so once that happens, the new horizon will be at a different position, and this event will not be visible anymore. Okay, so this is the simple gravitational dynamics in this case. Of course, here I'm reminding you of the relationship between the Euclidean and Lorentzian versions. So if you have a Euclidean black hole, there will be a boundary in Euclidean space that is some region of hyperbolic space. In fact, it will be a circle in hyperbolic space, and that corresponds to these two lines in Lorentzian signature, two particles accelerating away from each other. And of course, it corresponds to the thermofield double of some dual quantum system. So now, so far we discussed what happens when you send in particles from one boundary, and now we'll discuss some other effect that occurs when you put some interaction between the two boundaries. So imagine that we have these two boundaries. They are evolving independently from each other. And now we put in an interaction between the two. So we are adding in a term in the evolution operator, which is the product of a field here in the left side and a field here in the right side. We could imagine doing this in some hypothetical dual system where this would be operators in the dual quantum system, or we can, for the purposes of this picture, we can think of this as two interactions between two bulk fields that live. They are the boundary values of the bulk fields at the position of these boundary particles. So from the point of view of the bulk, from the point of view of the interior of this idea space, this looks like a non-local interaction. But if we were thinking about the local, about the dual, let's say, quantum theory, we could imagine these two quantum theories in the thermofield double living in some lab, and then we just couple them to each other. Now we can take this interaction and approximate the effects of the interaction by just taking the expectation value of these fields. And if this is the same field in the thermofield double or in the black wormhole, they will have some non-trivial expectation value. So we'll get some extra phase. And this is something that will depend on the distance between these two particles. And therefore, it will give rise to a force. And if we turn it on at just one particular time, it will be just simply an impulsive force, so present only for one instant. And by choosing the right sign for G, it can be attractive. And if we turn on an attractive force, then it kicks the trajectories inwards. So instead of outwards, it kicks them inwards. And what that means is that now the new position of the horizon will be sort of deeper inside. So there was an event here which was not visible before, and now becomes visible due to this effect. Okay. So this same effect means that if we send a signal here from the left side, and we add this interaction, now this signal will be visible from the right, and the wormhole has been rendered traversable. And of course, this is no contradiction with the statement that wormholes are not traversable in general relativity, because we are putting this non-local interaction between the two boundaries. So there is not there isn't any surprise about why this, you can send signals between the left and the right side. What is surprising is the manner in which the signals are sent. So that picture that we saw before is a little picture of a cat, and it looks very scared. And the reason he's scared is because the cat has been told that he was going to be dropped into a black hole. So that scared him. Then he's told, oh, don't worry, you're going to drop it, but we are going to extract you. We're going to make it traversable and so on. And so the cat thinks that what will happen is that he will be dropped into the black hole and then it's going to be squeezed into this boundary interaction, very deformed, sent to the other side and perhaps hopefully reconstructed. So that's what the cat thinks is going to happen to him, and he's very upset about this. But the cat has a very smooth sailing. He feels nothing particular when he falls through this wormhole. He just feels he's falling in empty space and nothing special. In fact, no animals were harmed during this experiment. Now, there is a slightly simpler protocol for this process, which involves dropping the cat. And here, instead of setting up the double trace interaction, we just make a measurement. So we measure some field phi, and we get some results, some eigenvalues for the measurement of the field. And then we just simply send classical information from this boundary to the other boundary. And here, then we act with an operator which involves the result of the left observation and the right operator here that is correlated with the left observation. And from the point of view of the right, it turns out that this process generates exactly the same effect because, it generates exactly the same effect whether we here measure on the left side or not. So we could imagine that we could have done the previous process, and then, let's say, someone measured the left side, and the answer here from the point of the right observer would be exactly the same. From the point of view of the left observer, it's not the same, because doing the measurement creates some disturbances, which, as we saw before, they perturb the trajectory of the left boundary particle. But from the point of view of the right, it's exactly the same. And this procedure is basically a particular instance of quantum teleportation. So we are making a classic, we have an entangled state, which is the thermofield double. And on this entangled state, we are doing a measurement. And then we are sending the classical information to the other side, and then doing some extraction of that information. So information effectively is transferred through the entangled state. There are some very minor differences with the usual teleportation discussion. One minor difference is that we do not need to measure the left state completely. And the other minor difference is that the encoding and decoding operations are done doing the standard Hamiltonian evolution in this system. It's important for this that the Hamiltonian is chaotic and so on. And as usual, there is a bound on the information we can send, so the number of classical bits needs to be bigger than twice the number of qubits we want to send. Now, let me just briefly discuss the origin of this bound from the gravity point of view. So if you attempt to send, so imagine you have the left boundary, and now you send some information. We're going to do the same procedure as before, so we're going to send the information. But now we are trying to send a lot of information. So as we discussed, when we send something in, the boundary trajectory gets a little kick outwards, and so far we have ignored that kick imparted by the information we send, but if we take it into account, then the trajectory is going to be slightly different, and by the time we make this measurement, or either we do the double trace interaction, we'll find that these two boundaries are going to be further than you thought because of this kick, so the correlations will be weaker, the force will be weaker, and the effect will be smaller, and instead of going where you were going before we took into account the back reaction, now we'll have a smaller effect and you will not make it to the other side. Okay? So we don't open the wormhole if we don't open the wormhole enough if we are trying to send too much information. Now, these were all pictures, but behind these pictures there is a precise formula, which is this one, which is telling us how how this information is being transferred and so on. So I'm going to just tell you what the elements are behind this formula and how one can derive it. So here we have the double trace interaction that we mentioned in terms of the two insertions of the field on the left and the right. And there is another field, chi, which represents the quantum information we want to send. Previously in the pictures was depicted by a cat, so here we have something simpler, just a quantum field. So what we do is we Fourier transform the signals we want to send, and the correlator B, so depending on the Fourier mode, so that variable is judiciously chosen so as to be the SL2R, to be conjugate to the SL2R generator that is most responsible for kicking the trajectory outwards, that has the most effect. And then this correlator that appears here will be evaluated on a background with momentum P. And that effectively gives a P-dependent SL2R transformation on V. So that was the displacement of the trajectories. And of course, all these effects, these effects are amplified by chaos or the exponential deviation of trajectories in ADS2 space. And then we get an extra phase from the expectation value of this V. So the final formula is just the Fourier transform of the signals. So that will be, this first factor will be just without taking anything into account, with setting G to 0. We would just have this, the 2-point correlation function between two sides of the thermofield double. And then the fact that V is evaluated on a background, on a trajectory that has been kicked, is related to the appearance of this extra factor here. So the first factor comes from the first expectation value and the second from the second expectation value. And we see the amplification effect, we see the effect is proportional to G Newton, and so on. And this formula includes the effects of gravitational back reaction and the fact that the wormhole closes when you try to send too much information. So there is a slightly, so what there is a simplified limit where we ignore the effect of this effect that when we send in the cat, the signal, the brain gets kicked a little bit. And in that, there we just expand this denominator, and we get a formula. So the leading factor of G cancels, and we just get this. We get a term of this form. So in order to expand this denominator, we're assuming that this is small, but G is large. So we have to have either G is large means that one way to achieve a large value of G is to have a large number of fields that we're correlating. So that's the large amount of information we send from the left to the right side. And if that's large, then even though this is small, this net effect can be large. An important part of this is that this formula contains this factor, and then P, remember, was quantity conjugate to one of the SL2R generators. So this is just saying that the net effect is a particular SL2R transformation. So it's a symmetry of the system, and so that's why the cat is not feeling anything special when he's going through the wormhole. And so this is related to the fact that in 2 dimensions, shock waves are not felt. So in higher dimensions, when you have a gravitational shock wave, you can have some tidal forces, but here you don't. This is something special to 2-dimensional spacetimes. Now, everything that we said depended only really on the motion of the boundary, and that was related to the Schwarzian action. So everything we said is also true in the SYK model. So as Douglas discussed, we start with the SYK model. We can think in terms of the fermion 2-point function that roughly is the same as the metric in ADS2. And then we have some low energy variables governed by the action, the Schwarzian action, and they couple to fermion 2-point functions and so on in this way. So the point is that we got the same action for the boundary degree of freedom, And everything we said about the motion of the UV boundary and so on also holds for SYK. Now we can say it in terms of what the Schwarzian action is doing. But we'll have the same traversability effect in SYK. We have exactly the same formula we derived is also valid in the SYK model. So we have a quantum mechanical model where these results also hold. Now for this model, it's a little bit convenient to define spin operators by combining a pair of Majorana fermions. So these have plus or minus eigenvalues. And we can, for example, write the double trace interaction as the interaction between these spin operators on the left and on the right. So in fact, there is, let me now change track slightly and we'll connect it back to what we were discussing in a second. So let's imagine you asked yourself, can I describe the pure states in the SYK model? So normally, well, in the previous talk, we discussed mostly Douglas discussed mostly the thermal ensemble and thermal states in the SYK model. But so one way to produce pure states is to measure all the spin operators we discussed, get the eigenvalues, and get the joint eigenstates of all these operators. So that's one particular way to generate particular eigenstates. And of course, this set generates the full Hilbert space. And, but those have relatively high energy from the point of view of SYK, have energy close to 0. And normally, we're interested in lower energy states. And so we can project onto lower energy states by doing a little bit of Euclidean time evolution. So we do some Euclidean time evolution on these states, and we'll project onto lower energy states. So this is a pure state, a relatively low energy pure state. Now, it turns out that the fermion correlation functions on this state look actually the same as the fermion correlation functions in the thermal state, and up to some corrections that have to do with the fact that we are doing the disorder average. So this follows from the fact that, from the following fact. So this, when we average over disorder, the model has an ON symmetry, and there are some particular ON transformations that flip the sign of the spin. So the ON symmetry says that whatever the result of this is, it should be independent of the state because we can flip it by doing an ON transformation. On the other hand, if we sum over all these states, we get the thermal state because that's the full sum over the whole Hilbert space, so we get exactly the thermal state. Therefore, they are all equal to the thermal state, up to corrections that have to do with the fact that the proper way to treat disorder is to do the replicas. Okay? And there are some off-diagonal correlators, so correlators with fermions with different indices. Those are different from the thermal state, but they can also be expressed in terms of some other thermal state two-point functions, so through a similar argument to the one I just given. So these are particular pure states for which we can compute the results precisely. Now, another way to think about these pure states is that we are imagining the thermofield double, and we do a measurement of all the fermions on, well, all the spins on the left side, okay? And there we are projecting onto one of these eigenstates. And then we did the Euclidean evolution by beta over 2. And so we can consider this configuration and look at the Lorentzian dual of this configuration. And the Lorentzian dual would be a black hole here, the black hole we had on the left, on the right side. And on the left, we did this measurement that is introducing some kind of shock wave or some end of space. We don't know what happens beyond that. I should mention these are some configurations in gravity that have the same symmetry properties as the SYK model. We don't have a precise dual to SYK, so these pictures are not precise duality. They are just a picture of what we expect the state to be. And so in these particular states, there is a region outside the horizon that we can see, and there is some region that we cannot see for all these pure states. We can add some bulk particles by adding some other operators here, and again, we can do this both in gravity and in SYK, and the determination of what the state is just purely determined by the symmetries. And so whether we can see it from the boundary or not is again determined by the symmetries. And so there are some particles you can put here in the interior that you will not see from the boundary, and there are some that you might see from the boundary. Now, it turns out that you can see behind the horizon, and one way to see behind the horizon is to add an interaction to the model. So an interaction which is similar to the double trace, essentially the same as the interaction we're adding for the double trace problem, and that will modify the trajectory, and you can calculate this modification, and the modification is such that you can see the whole region behind the horizon. So this is exactly the same effect that we saw in the traversability discussion. And well, these are the formulas behind what I just said. I won't. And finally, let me close in the last couple of minutes on the relationship to the black hole cloning paradox. This is a paradox where you imagine an old black hole, and Alice goes in. Well, this is an old black hole, and Bob has a copy, has a state that is perfectly entangled with the old black hole. And so he can collect some Hawking radiation. Sorry, I'm trying to hurry too much. So Alice goes in and sends a message, and this message can be extracted relatively quickly by Bob by looking at the few qubits of the Hawking radiation, if the message had a few qubits in content. And then there is an apparent paradox because the message appears to be duplicated, so it seems to be both in the Hawking radiation and in the interior. Okay? So Bob sees two copies. Bob might see two copies when he goes in. And one of the answers to this paradox is that, well, he has to wait some time, and maybe there is a trans-Planckian problem in sending this message. And so okay, there isn't an obvious problem, but the problem seems to be cured by the fact that, well, it involves trans-Planckian physics, and so it's not clear why. Now, in this case, we can think of Bob's computer as a black hole, which is in the thermofield double, and we can look at the same problem by thinking of Bob's computer as being a second black hole, and Alice's black hole, the original black hole on the right. So if Alice sends a message, if you look at the picture here in the thermofield double, the message is only in one place. So there is no duplication in this picture. And if let's say Bob gathers some Hawking radiation and fits it into his computer, that process can be thought of as similar to this setting up of the traversable wormhole, and that kicks the trajectory of Bob's black hole inwards, and then then he can get Alice's message. Okay? So that's how we understand that process, and the fact that seems surprising in Hayden and Preskill's analysis that this process can be done relatively quickly and with a small amount of information. Now, if Bob can get the message, then Alice, if she were to evolve the system backwards after this double trace interaction, would not get the message back. So Alice lost the message, and Bob got the message. The message is only in one position in the whole picture. And well, I think I ran out of time, but you can also consider a more complicated situation where Alice sends a machine that then sends the message here to the right, and then if Bob does this, then he will get the empty machine, but not Alice's message. But he can extract the machine here, and then evolve the system backwards without the machine, and then he will get the message back. So this would be the recovery operation for Bob in this picture. Okay, but in this whole discussion, only one copy of the message is present. So the message is never duplicated, and the process of extracting the message puts it out of Alice's reach, and there is no need to involve trans-Planckian physics to solve this non-cloning problem. And everything is understandable from the standard rules of gravity on the wormhole geometry. Of course, you have to assume that entanglement means that there is a wormhole. So maybe you can say everything is hidden in that assumption. So the conclusion is that we have a simple picture for gravitational dynamics of nearly ADS2 space. Traversability has a simple origin. Nothing special is felt by the traveler. and there is a connection between traversability and teleportation. Traversability in SYK has the same description, so it's a quantum mechanical model where this phenomenon is present. It's consistent with information transfer bounds, and we saw how one can construct a full set of pure states which appears to have a smooth horizon. So this is a set of microstates which is rich enough to give the full entropy. And we showed how to look at the whole region behind the horizons using a phenomenon similar to traversability. Thank you.
Yeah, many thanks for your nice talk. Still we have time for questions.
So do I understand correctly that in all these experiments, the amount of entanglement that's taken out by this double trace is order 1 in units of n?
Yeah.
What would happen if you wanted to disentangle the thermal state completely? The geometric picture would break down? Is there something that one can do to understand?
Well, one example was this, this example where you measure the state completely, right? So you measure completely the state on the right, and the picture is the one I was mentioning. You end up with a pure state, right, that has some kind of shock wave behind the horizon.
But then the geometric picture doesn't exist till some region in the region inside the horizon. There's some.
Yeah, but it's behind the region where it does not exist is apparently behind the horizon at some finite distance behind the horizon.
Right.
Other questions?
So the central point here is so central point is that this region where the geometry ceases, well, there might have some problem, is behind the horizon. It's not at the horizon.
More questions? Can you wait a second, please?
Just a quick clarifying one. So at no point in your no cloning statements did you have a space-like slice that would have seen the message, or did you have something that the single message was sort of meandering back and forth in time?
Mm-hmm. I didn't get the question.
Did there not exist a space-like slice on which you could have multiple copies of Alice's message?
No. So in the bulk, there is the space-like select. There is only one copy of Alice's message.
On any space-like slice?
Yes.
Okay.
Yes.
All right. So if I do not see any more questions, we thank Juan again.